Right. So hello everybody. So as Ruben said, sorry again. It's again a talk on about improving performance of application under Mono. So, well, actually that's a good thing. So my name is Jeremy Laval, and actually I would like to note that the work. So I implemented ParallelFx for Mono. And I would like to say that this work was part of actually Summer of Code, Google Summer of Code. So first of all, I would like to thank Google and Mono for allowing me to work on such a cool project with such cool people. And well, so in my talk, I'm going to first talk about why actually we have to bother with all this multi-threading stuff. Then I'm going to talk about how we can actually use that to improve performance in all range of application. And then I will focus on ParallelFx in itself, showing what you can use in ParallelFx, what is all the tasks, or works the scheduler, or works spelling, which is a really nice part of ParallelFx. And finally, what's the state of thing actually in Mono? So how much it is implemented actually. So first of all, why are we bothering with all that parallelization stuff? The thing is that everyone loves a single-threaded application because we have been taught to program like this. And I mean, every language, pretty much every language, works on a single thread when you code. But as a wise man said, the ideal number of threads you should use is 1. So I agree with that, but we are going to see that it must have a special twist about it. And again, we are bothering with parallelization today because the free lunch is over. I will explain what is exactly the free lunch, but basically the thing is that we need to change the way we code. We have to throw away a bit our point of view of all serial programming. So what is exactly the free lunch? From about the 70s to 2005, chip manufacturers were focusing, when they were producing CPUs, basically they were fighting over the clock speed of the CPUs. So that was really cool because basically programmers could write a program, say like in 1995, and it would run pretty well. And like 5 years later, actually maybe so by Moore law, I think it's like double architecture. So basically the year later, the clock speed of the CPU would have doubled. So basically your application would be twice faster than the original. So that was pretty cool because you had to do pretty much nothing. And as time goes on, your application just becomes faster. But of course, it's not a paradise because at some point you have the physical limit of actually the chip. I mean, you can't put too much transistor. We have arrived actually, so about 2005, and you can actually see on the curve because from about the 70s to pretty much 2005, we have pretty much straight lines. So it's like the clock speed actually increases each year. But we are on a point that we can't pretty much accelerate anymore your CPU. So manufacturers had to find another way to actually remain competitive in the field of CPU manufacturing. So the bottom line is that right now we can't count on that free lunch anymore, and we have to change our way. Clock speed war is a no-go. So the awesome idea that Intel folks and AMD folks had was, well, we can scale vertically, so let's just add more core and scale horizontally. But of course there is a problem because, and actually, so they decided to do that first by putting like 2 core in 1 CPU. So that was, at first we had like the range of, sorry, I'm using Intel name, but well, it would be the same for AMD, but basically we had the Pentium line, which was only 1 core. Then they introduced the Core Duo, which was like the first dual core processor. Then they moved on like quad-core processor, and now recently they have released the i7, which is like 8-ish core. Basically, it's like they are 4 core, but each core is like hyper-threaded. So for the system, it's like there is 8 core. And now they are even designing prototype, which has 80 core. The thing is that, so basically we can't take advantage of all that stuff like the way we used to with clock speed. Because your application isn't going to be faster as the number of core increase. You have to do something in your application. You have to actually break up work so that you can have separate tasks. I mean, you have to separate actually your work in multiple tasks so that actually each of the core in your processor is doing something. So the solution to actually remain competitive also in software is to break up work and share it among cores. But as you can suppose, it's not really that easy. Actually, so as you can see, even a cat has problem doing multi-threading code. So yeah, the truth is that parallelization is a difficult thing. It's hard. So as Alan said, you have to manage your thread, you have to manage your lock, you have to be careful. Is that part of the code? Can it be called by multiple thread? Am I taking the lock in the right way? Am I releasing them in the right way? Because it's tedious to do that. I suppose everyone who has ever done multi-threading programming at some point had to debug deadlocks. And I'm pretty sure we'll agree that it's not a really nice business. So, and finally, it's also most of the time inefficient to actually manage the thread yourself. Because actually the question is, how many threads should you use? Because if you use too few threads, like say you are developing, you have a 4-core machine, but you use like 2 threads, you aren't going to use all your core. So basically it's under efficient. But then if you use too much, like you are using 4 threads on dual core machine, basically you have, so actually the operating system can only run 2 threads at a time. So if you have 4 threads, it's going to change, at some point of time, it's going to change the thread which are executing. And that creates a lot of context switching. And if you use too much thread, actually the context switching, the cost of context switching your thread costs more than the actual optimization of running it in parallel. And again, that brings this point that what if the number of cores change? Because you could develop your application on like a really big box with like 8 cores. But again, if you ship it to a guy who only have this small dual core or even one monocore, it still exists, it's going to actually perform very badly. So, well, that's getting complicated. So we need some key principle in that. We need really something different, something that should automatically regulate thread usage at runtime. Basically, like we went from compiled code to interpreted code, or like JIT code, JIT compilation, because we want to be able to optimize the code at runtime for a specific machine. And actually, we have to find something analogous to that for multi-threading programming. And the second point is that it should be as straightforward as possible, because as I said, most people are used to the way they code. The way we are taught to program is really sequential. So the shift from sequential programming to parallel programming should be as painless as possible if we want people to adopt this kind of programming. So it should be ever mimicking familiar construct. That is to say, well, in ParallelFx, for example, we have the parallel loops, which act like any for loops you have been using for ages. Or it should reuse existing code with only slight modification, like one method call, just an added method call, for example. So, answer ParallelFx. So ParallelFx is like, it was developed by Microsoft like in 2 or 3 years ago. And actually it was supposed at first to be bundled as a separate library. But actually it seems that it's going to be part of the whole .NET for platform. And actually ParallelFx is integrated in Colib, so the very heart of .NET. So how is ParallelFx? Basically you have this part, which is the actual primitive that you can use to use parallel programming inside your application. And the smaller part is like, so the really lower level part is all the scheduler, and it's actually a really nice piece of technology. I'm going to talk about it later, just after. And then you have like almost 3 building blocks that you can use, low level building block, which is the task. So the task is basically like thread, like you would use your normal thread. Future is like just build up on that, and actually, well, I'm going to talk about that later. So we have parallel loops. Pairlink is like, I hope everyone is familiar with Link. Anyway, if you have seen Miguel talk, you should be familiar with Link, so I will just say that you've seen Miguel talk. So, which is actually a parallelized version of Link. And then, of course, we can't do like this without any helper class. So basically, we have a whole new set of collections that are thread safe, but which shouldn't use, thread safe collection, and also a whole new set of coordination data structures, so lock and all that sort of sub-barrier, well, any kind of thing that you could use in a multi-threaded environment. But again, they are really specific because, like for example, the concurrent collection, they try to don't use lock because lock is really inefficient. So it tries to actually be lock-free, what we call lock-free code. So yeah, so let's speak a bit about actually the scheduler, so which is the heart of all the ParallelFx library. Actually, the scheduler is a really nice piece of technology because instead of just creating, like you would say, instead of creating a thread for each task you do, basically, I mean, some guys said earlier with Alan that basically the number of threads you should be having in your application should be equal to the number of core that the computer has. This is really true. So actually, ParallelFx build upon that, and it always manages an amount of thread that is equal to the number of core you have on your computer. But of course, it should also be able to handle like 1,000 tasks at the same time. So you have to make a trade-off. You have to run 1,000 tasks on one hand, but you also have to keep only 2 threads. So actually, the scheduler is built on the work stealing principle. Basically, a mono application feed the scheduler some task, which first go into a shared work pool. So then the thread worker, so the thread worker is like simply a worker which wrap up an OS thread. So an OS thread is like system thread. And then it takes up that work. And really the cool part of it is like, so let's say that, for example, you feed 100 tasks to the scheduler. Then each thread worker, so if you have 2 thread workers, let's say that each thread worker process like 50 tasks. The thing is that most of the time, tasks do not take the same time to execute. That's the whole point of it. So if it was just like the thread worker took some work and then execute what he has, basically you had one thread worker which at some point run out of task. So you would have one thread worker which continue executing, and basically you would have one thread which is wasted because it does nothing. So the cool thing is that in ParallelFx, when a thread worker has no more work to do, he will try to seek work to do in other thread workers. So that's the steal part. That way, every thread at any time should be still processing something. That way you get the maximum performance out of your code. Yeah.
What's the reasoning behind keeping a local work pool? Can't they just each pull one job at a time from the shared one?
Actually, so as I said, the problem, basically you could do your work only with a shared work pool. So a shared work pool is like a normal collection with a lock, basically.
That's getting a bottleneck.
Yeah, that's a bottleneck. Because actually, as I said, ParallelFx should be able to handle like 1,000 tasks at a time. So if you do like 1,000 times, acquire a lock, release the lock, you are going to kill your performance. So what we must ensure is that you have the maximum locality. What we call locality is that basically a thread worker in normal operation shouldn't be doing any locking, any interlock method, any call like that, any synchronization stuff. So what is that a thread worker should only work on what is local to him. And actually, only the steal process actually do some locking, or it's not locking, actually it's using interlocked CAS. If anyone knows CAS, what CAS stands for, is doing CAS work. So that scheduler is really the heart of ParallelFx, and actually it's so efficient that basically the thread pool in .NET 4 is based on that scheduler. Basically, if you are using thread pool, like if you use thread pool before .NET 4, it was like if you feed a task to the thread pool, you will create a thread for each task. But that was pretty inefficient because if you create a lot of tasks, well, you just blow up your machine. So now in .NET 4, actually, when you queue up a task with a thread pool, it actually creates a ParallelFx task and just feed it to the normal scheduler. And actually, so it's not the case at the moment in Mono, but we are pretty much working on it. We are trying to integrate that. So hopefully in some time we should have also in Mono a thread pool which work on that scheduler. So now let's speak about each way you could actually parallelize your things. This is like task. So task, you should use it like any normal thread. Basically, a task is like a small a unit of work in your application. So that's a kind of traditional way to use a task. Basically, you may create what is called a cancellation token source, which basically handle in ParallelFx all the cancellation stuff. In ParallelFx, cancellation is like at the heart of the framework because every operation, so be it task, wait, well, any kind of operation can be cancelled at some point of time. So instead of having like on a task a cancel method, for example, they made a more generic framework building a cancellation token source. So basically, you always have a source of cancellation, and then you pass around some token. And you can actually pass the same token to multiple method call. That way, when you call actually cancel on the source, it is able to cancel multiple work at a time. And then you can chain together multiple cancellation token source. That way you can, well, handle really pretty nice, pretty neat stuff about cancellation. So basically a task is pretty much used like you would, a task is created pretty much the same way you would use the thread pool. You just call a factory object, and then start new, and you feed it with like a function, and basically it will try to execute that on a separate thread. So the method is called non-blocking, so you just continue your execution like a normal thread. A neat stuff also, which is available, is all the continuation philosophy. A continuation is basically something, so you will take basically the scheduler, it's like a callback actually. It's like, when you finish this task, I want you to run that thing too. And again, it's really just a task. So again, it can be scheduled on another thread. It can be completely scheduled on another thread. And that's all. Well, you have some method also to wait, of course, on it. Then you have the future, which is really an interesting way to program. Future is like, actually, it's a shift of mind, because future should be used like, you have some sort of calculation going on. And basically what you should do is like, instead of actually calculating a result of your computation, you should say to your code, okay, I'm doing a computation. The thing is that I don't have yet the result. So I'm going to give you, instead of giving you an integer, I'm going to give you a task int, which basically say, I'm computing the value, I don't have it yet, but just use what I give you, and I promise that at some point you will have a value. And this is very neat stuff, because of course a future is like a task. So what I say about delayed execution is that it gets executed on another thread. And the cool thing is that you can actually chain future together. So you never actually process anything, but at the end, when you need the value, it's going to get processed automatically on several threads. Like for example, here you have a tree, so it's basically a method which you have a tree of integer, and basically it's a method who will try to calculate the sum of each element of the tree. And you can actually see that the right part of the tree is actually done. So yeah, the right part actually is done like normally, sequentially. But then the left part of the, so all the method is actually, recursive. And actually the right part of the tree is like taken as a result, but the left part of the tree is calculating here against start new, but with a future. So basically all the left part of your tree will be chaining up future together. That called later value. So like value is a blocking call, but basically by the time you have finished calculating the right side of your tree, the left side should have already been computed because the future is executed on another thread. And so you can chain up, and the cool thing is that of course you have a relationship between each future, because the futures depend on another future, which depend on another future, etc., etc. And it's handled by the runtime, so that actually when you request the value of the topmost future, it will just walk down all the way down and get the result from the lower level future. So this is, you have to change your code actually to make use of future, but it's a really nice way to program. Then you have one construct which is really used a lot, which is the parallel_for. So again, when I said earlier that ParallelFx should be able to mimic existing construct, this is one of the constructs which, everybody has ever done a for loop. And the for loop is actually something that you can really easily parallelize. Basically, you say that each thread should be doing like, if you have a loop which goes from 0 to, 1000, basically if you have 10 threads, you should just say like thread 1 does the work from 0 to 100, the other thread do the work from 101 to 200, etc. So it's very easy to parallelize. And actually parallel_for just does that. It tries to partition the range of value into smaller range that each task can process individually. And actually the really cool thing about parallel_for is that, as you can see, it's almost the same as a traditional for loop. You just say parallel.for, where you want to start where you want to hand and what you want to execute with the value. And that's all. Behind the scene, it's all going to partition the stuff, parallelize your stuff, but you don't know. So that's one of the actually where I agree on Alan, saying that developers should really use one thread. The twist is that developers should think they are using one thread. And this is one of the ways to ensure that. Basically, the programmer don't care. He just writes that up and it feels like it's a normal for loop. But actually, behind the scene, without him knowing, it's doing parallel stuff. And it's actually improving its application. So, demo time. Actually, I'm going to use ParallelFx is really useful, as you saw here, for image processing again. Because basically, when you do image processing, pixel-based processing, you just iterate over the whole range of pixels you have in your picture. So an easy way to parallelize that sort of stuff is basically to use ParallelFx on the outermost for loop you have in your program. So actually, oh, sorry. Anyway. So here I have a little code which basically is a fractal drawer, and really the only difference you have between like a sequential, so that's all occurred, simple stuff. Basically the only difference between a parallel version and the sequential version is that the for loop you have here in the sequential version is just changed to a parallel for one. So basically the only difference you have is like modifying this line and this line. 2 line change and you get most of, so like I have a dual core processor here, and you get twice as much performance as the sequential version. Don't take my word for it, I'm going to show you. So here, I'm going to run it in, so this is the sequential version. So, of course it's heavy usage. I mean, parallelization is very good when you have either a large data set or if you have like method which takes a lot of time, so Ayobun method, for example. So if everything goes well, here you go. So like 26 seconds to actually produce that stuff. Of course, you can criticize my art skill. I'm actually not an artist either. But basically, this is like a fractal, a Mandelbrot fractal. But it's just for the point of having an EV calculation. So as you have seen, the processing of that stuff took actually like 30 seconds. Now let's run it in parallel. So again, I say it with a 2-line change. So now I'm using the parallel for loop. Still taking some time. Here you go. 15 seconds. 2-line change, and you have approximately like 10 or more second speedier program. 2-line change. And actually the same output. So, sorry, it's going to take some time to go back to where I was. Sorry for this.
It sounds like there wasn't coordination between the two talks, yours and Alan.
Yeah.
Maybe it doesn't.
Maybe for the cat. That way, if you hadn't understood anything, you can just see everything back. A speedier presentation. So that was around here. Okay. So here I spoke about actually the lower level stuff of ParallelFx, which are so the tags, the future, and the parallel loops. So actually, I showed ParallelFx, but you have actually also a ParallelFx. So you can also parallelize any for each loop, which basically iterates most of the time on collection or link request actually. But to do that actually, so speaking about link, you can have also very neat stuff which is called parallel link. Parallel link basically take up your link query. So I hope everyone is familiar with link again. I hope. So basically, a link query is like you put up some operator and you say, I have a data source somewhere and I want to apply some operation on it. And basically what parallel link does is that it takes up the query, look into the query where which part could be actually parallelized because either it's running slow or there's a big data set and that sort of stuff, and actually try to parallelize it. The whole point of parallel link is that if I remove that part, it's actually standard link. And the only modification I did to actually parallelize my query was just adding this line. So you can ever, on any link query, basically, ever you had this small operator which is as parallel, or you just use the parallel enumerable class instead of the enumerable class to like creating a range enumerable or repeat enumerable. That's all. One line change or even less than one line change and you have your parallelized query. So again, demo time. So a very famous example. If you follow Microsoft guys, you probably have stumbled on a guy which is called Lukoban. And basically he likes to do crazy stuff. And the latest crazy stuff he has done is this. So I showed you like a link query, but it was very small. But this is actually a whole ray tracer application only written in link, in one big link query. All of that stuff, and actually it's not finished here. You can go down here. All of that is a link query which basically do ray tracing.
That's what I said when I said that C# now was going functional. That's what I meant.
Yeah.
One of the things that he's been saying is, the idea is no longer to have side effects. Is that everything that basically you don't mutate the global state. Everything is local, so that you can parallelize these things. And, this is one of the things that you can do.
Yeah. Of course, yeah. I should say that really functional style programming is really sweet to actually parallelization because. When you parallelize stuff, you really don't want to have any side effect or shared state. So when I say that the programmer basically have to change while line, well, it's not totally true. You also have to be careful on what you're actually doing in your function. Because if you are doing like any work on a shared state or like a traditional collection, for example, you have to protect it with lock or anything. But to moderate that, actually I showed you that we have actually concurrent collection, which are very efficient in a multi-threaded environment. So instead of using your traditional collection, just use that and you will have no problem. But yeah, again, so basically you have this enormous query. And then what it takes to parallelize it is basically just changing enumerable to parallel enumerable, which is a 1, 2, 3, 4, 5, 6, 7, 8 character change. So actually the pelling stuff is not really finished. I'm working on it. It should be hopefully ready by Mono 2.8. But anyway, I'm going to show you what it does look like at the moment. So here I can select if I want to run to actually process the thing in sequential manner or parallel manner. So I will just first do it in sequential way. So it's always black. Okay, so it's coming. So actually notice all the thing is processed. Basically, it's like a for loop, you would say, and it basically for each pixel process calculate what the color should be. In essence, it's that. So actually, as you can see, it's pretty much going it like in a linear fashion, and that actually takes up some time. A lot of time. The thing is that basically at that part you have all the reflection which is going on, which is a lot of actually recursive function. So that's actually the hard part of the picture. But I'm going to stop it here. So really just for you to see how ParallelFx works or P-Link works. So now if I select the parallel version and render it, basically what you are going to see after some time, here, you actually see that the image is being not processed like as a wall. You have some black line here, which actually it showed that there is actually 2 threads doing the work. Basically what P-Link does is that it takes up the whole query. See that you can partition the range of pixels of the screen, and then it fires basically a task to process alternatively each part of the screen. So basically this thing is twice as fast. Again, on my dual core computer, because I have 2 core, it's twice as fast as the other way. You're actually seeing it's quite faster than the other. So again, take some time. So yeah, let's speak about state of things. So actually, ParallelFx, so as I said, it's quite an old project now, because it's actually, I have spent like this summer, my second summer of code on it. So it's actually a 2-year project, 2-year-old project. And basically, the first version of Mono to include some ParallelFx bit was like 2.6, which was released some month ago. I'm not really sure about the date anymore. And so it shipped with a .NET 4 Beta 1 API. And you get all the tasks, future parallel loops, concurrent collection, and coordination data structure. So pretty much, like I would say, 80% of the framework. The only part missing is actually the pailing stuff I'm still working on. And actually, in Monotrunk, so about a week ago, I completed like the beta. So between .NET 4 Beta 1 and .NET 4 Beta 2, there is some change in the API. And basically, in Monotrunk now, the API is fully Beta 2 compliant. And at this point, normally, between .NET 4 Beta 2 and .NET 4 Final, there shouldn't be a lot of change. So actually, if you want to start already using ParallelFx, you're probably safe by using the trunk version already, the API of the trunk version. And so hopefully, by Mono 2.8, we should have fully .NET 4 compliant API with P-Link. So thanks for your attention, and if you have any questions, I'll be happy to answer.
So,
Yep.
can we, every for loop in our program that doesn't have side effects, can we sprint it on it, or is there an overhead penalty that we should take care of?
The thing is that parallel programming isn't magic. So actually, maybe sometimes it's actually the cost of actually scheduling tasks is more expensive than the parallel optimization. So I would say that you are safe if you are like processing big chunk of data. So like image processing, well, a lot of things. Basically, like we were talking with Bertrand the other day, and there is like in Banshee, for example, you have an extension which is called Mirage. And basically what Mirage does is that it analyzes all the songs you have in your library, your music library, and then it computes basically the similarity between each of your songs. So actually in this kind of application, so like a fairly standard desktop application, each of this processing of, each song processing actually could be represented by either a task or a feature. I would say more a feature. So you could have, even if you have like 10,000 songs in your library, you have actually 10,000 feature. And it's only it's not going to create, you couldn't use like a thread pool, for example, because it would be like creating 10,000 threads, which probably will blow up your machine. But if you use ParallelFx Future, basically you are only running on 2 threads, and you are still processing your 10,000 songs. So that's actually a neat usage of Future in like a desktop application. So that should be. So actually, don't take my word, see for yourself, try it in your application. The best way to actually see if it's speed up thing is to try it in your application. As I hope I have shown you, it's really easy to actually plug any parallel behavior in your existing application. So test and report any bugs. That's important. Yep.
If you have any variable implementation, what kind of heuristic is it using to decide how to channel the range?
Yeah, so actually, yeah, there is like several heuristics in parallel link. Basically, if you feed up with like a collection which can work on index fashion, it's going to basically strip the whole data range small chunk that you can actually access. That is the fastest way actually to use paralleling. If you are using it with like an array or a list or basically anything which work on an index, it's going to be really fast because we can access each element of the collection without any overhead. When we are doing this kind of partitioning, there is no lock, there is no cast, there is nothing. Everything is cleanly, each task is cleanly separated in its own environment, you could say, and has its work to do. That's all. But again, yeah, if you use like a standard enumerable, there you must have some locking because you can't know what the user is actually doing in its enumerable. It could be like another link query, for example. So maybe it's not thread safe. So in that case, we have to use, that's a shame, but we have to use locking.
You kind of put things into small
chunks, yeah.
How do you decide what is small?
Actually, yeah, that's, well, the thing is that, so basically, like if you, like at first, for example, like in the ray tracer I showed, basically how it was split up data is like it would have, one task would have done the upper part of the image, and the other task would have made the lower part of the image. But as you saw actually on the ray tracer example, the upper part is really fast because there is no reflection inside. But the lower part has more reflection, so it's actually, it takes longer to process. So at one point you will have one task which run out of pixel to process and will die. So actually the thing is that we have to make smaller chunk, so that, as you saw, it's like doing chunk like this at the time. Because in the end, hopefully it's going to, stabilize on the same amount of work between the two threads. The thing is that there is no, precise way to actually know how long a given function is actually going to take, how much time it's going to take. So we have to make some guess here, and it's not perfect.
One thing that is worth noting is that the heuristics built into the system, they will take into account things like the load average. So if your machine is overloaded, it will not spin up a lot of threads until the load comes down. So it will take those things into consideration. The second thing is that the final version of the API allows you to plug your own heuristic system. So you know your data better. So you can give the scheduler a hint, and you say, well, I actually know that this, the beginning is going to be really hard. So at the beginning, just separate 1 and 1 and 1. But when you get to number 100, start giving chunks of 20, for example. So you can plug that into it if you want.
Yeah. And actually, as I said, ParallelFx is not just about executing the query without knowing it. There is a step of actually checking how the query looks like. Because, for example, you have some operator, link operator, which are, for example, take, which only, are interested in like the first part of the data set which is processed. So it doesn't care about all the part that is at the end, for example. So in that kind of case, if, for example, the checker see that there is a take operator in the query, it will just, use chunk partitioning, but like with one element at a time. That way, take is take will probably be happier with what he's seeking, and you won't waste time on what he doesn't really is interested in.
So, 1 second. There used to be a coffee break right now, but we're 15 minutes.